Okay, can I go? Yeah, all right. So we're going to continue with the Fourier transform today, Fourier transform properties. And the Fourier transform really is sort of a stepping stone to get to the Laplace transform, which is what we'll get into today. And if things go according to plan, I'll pretty much finish with the Laplace transform today. And then next week we'll continue with the discrete Fourier transform, the fast Fourier transform, and the Z transform. And so we'll see how that goes. So I expect to spend 3 more lectures on transforms. Okay, so the Fourier transform, as you recall from last time, is this transform where we're taking a Fourier series and basically taking the limit as the period goes to infinity. So as the period goes to infinity in the time domain, in the space domain, the coefficients, the discrete time values, which is the Ck equals k omega naught, where omega naught is the frequency corresponding to the time period t naught. The coefficients Ck come closer and closer together. And in the limit, what happens is that the Ck's form a continuous function. And so from Ck, we actually get a function of omega, which we'll denote as x of j omega. Now, actually, this is a formal, what's called a formal parameter. In other words, we're just using j omega to represent the fact that it's a function, it's a complex exponential. Okay, so in some books and so on, you'll just use omega, you'll see u, you'll see various other things, but we're just using a formal parameter. There's more of a indication to us. And this will become important once we do the duality in just a moment. At any rate, what's going on here is that the Fourier series coefficients get transformed into the Fourier transform, and this period t goes to infinity. So we actually go from omega naught the period again to omega. We just don't have the period anymore. It's not periodic. We don't have coefficients every frequency period, but we have the continuous parameter over here. So that's the Fourier transform. And what we saw was that the Fourier transform is defined by, I'll just write this down for you. So the Fourier transform is given by x of j omega is equal to integral minus infinity to infinity xt e to the minus j omega t dt. And then the inverse transform is given by x of t equals integral, sorry, it's going to be a 2 pi factor over here, right, 1 over 2 pi integral minus infinity to infinity x of j omega e to the j omega t d omega. Okay, so that's the forward and reverse transform, and we write this pair as x of t x of j omega, and this basically summarizes what we talked about last time. Given these definitions, it turns out that the Fourier transform has some pretty straightforward properties, and one property of it, one property discussed last time was linearity. And linearity basically says that if I have two functions, x1 of t and x2 of t, then I can take the Fourier transform of the sum of them as the individual Fourier transforms. So I can basically write down, in fact, if I have function x1 of t, and then that has a transform of x1 of j omega, and then x2 of t has a transform x2 of j omega, then ax1 t plus bx2t, where a and b are constants. The transform is given by ax1 of j omega plus bx2 of j omega. And this one follows right away from this definition over here, because as you can see, if I multiply axt over here, or ax1 of t, the a comes out of the integral. Okay, and similarly, if I take the sum of two integrals, integral of x plus y is integral x plus integral y. So these two properties immediately tell me that I get this linearity property over here. And that allows us to solve the first homework, quite straightforward. The first homework was to find the Fourier transform of ut plus, let me write this down over here properly. Somewhere in this pile, oh, it's over there. Right. So we want to find the Fourier transform of u of t plus 5 e to the at ut. So the way we usually find Fourier transforms usually is to not go through the formal definition, which gets complicated, but to use a table, because you can find these tables of transforms and people have already done the work for you. We just have to be careful of using it, and we use the linearity property with the table. So this is going to be the Fourier transform of ut plus 5 times the Fourier transform of the e to the at ut. And ut, if you remember, is the unit function. So the ut is this function over here. That's 1 over here and 0, and it's the integral of the delta function. So this is going to be pi delta j omega, which is the first part, plus 1 over j omega. So this one comes from here plus 5 times, and that's going to be the transform of that. So what you have to be careful is that this is going to be 1 over minus a plus j omega, and a is less than 0, because the transform for e to the minus at is 1 over a plus j omega, where a is greater than 0. So here we just use the negative value for a. So this is the answer. Okay, pi delta j omega plus 1 over j omega plus 5 times minus a plus j omega. A has got to be less than 0, otherwise it doesn't work. Okay, so hopefully you can grade that one. Okay, any questions about this? Here. So this should be basically a straightforward application of the Fourier transform table. Okay. So I'm going to go on to the next property, which is time shifting. Okay. Time shifting basically says that, I'll just write this down, if x of t corresponds to capital X of j omega, then x, okay, I don't know why, okay, x of t minus t0, I'm shifting x to the right, the function signal x, by the value t naught. Then this corresponds to multiplication by the value e to the minus j omega t naught of the transform x of j omega. So basically we have this factor over here, e to the minus j omega t naught, to the transform over here. And last time I did an example of using the delta function to show you how this works, and that's pretty straightforward. So the important part here is that we can deal with time shifting with just a multiplicative factor of e to the minus j omega t naught. Why is this important? The reason it's important, and we'll see this more again in the Laplace transform, is that imagine I have a system with delays. Okay, so what will a system with delay look like? Let's say I have I'll give you an example of a system with delays. Let's say I have a piston, and I have some water over here, and then I have this piston, and I'm pushing the piston like so, and then the water comes out the other end. So this could be like a squirt gun, you gotta if it's a warm day, you've done this squirt gun thing, right? Water pistol, you push a lever, and then a chamber compresses, and the fluid is expelled at a high velocity. This is scientific speak for you spray somebody with a water pistol. Okay, so the compressed fluid is going to come out. Now there is a time delay. I'm going to push this, and then it's going to come out of there a little bit later, maybe a few hundredths of a second later. That's a delay, right? So the output yt is going to correspond to input xt, but there's going to be some delay over here. Okay, so we're going to take the signal xt, and essentially the yt is going to follow the signal xt with some linear scaling. Okay, so if I push down here, the yt is going to push harder, it's going to come out faster, it's going to be linear scaling, but there's a time delay. Okay, how do we incorporate the time delay? It's e to the j omega t naught. That multiplicative factor is what we use for modeling the delay. So that's why we talk about time shifted signals. Now, in the case of a computer network, we don't actually have this. Instead, what we have is, let's say we have a router and it has some number of output queues, and this is the output queues going to different destinations. You have some input queue over here. If there is some source over here and the source is sending a burst of data, because of speed of light propagation delays, it's going to build up at this input queue or that output queue after some delay. So if I'm going to tell you the signal, which is the buffer capacity or the buffer occupancy of one of those buffers, that signal is going to follow the input signal with some time delay. So I can say the buffer occupancy as a function of time, which is the output signal, is following the input signal, which is x of t, and this is, let's say, is y of t, with some scaling. So if I'm going to compute the Fourier transform of the output, it's going to be the time delayed input signal. So therefore, I can multiply the Fourier transform of the signal, whatever that Fourier transform is, by the delay factor e to the j omega t naught, and that's how we model delay. Okay. So while this looks like a pretty, let's say, dry mathematical fact, in reality, this turns out to be a big deal. And the reason it's a big deal is because when you multiply something with this factor, it becomes very hard to compute the inverse Fourier transform. Okay, in the same case, when you do the Laplace transform, when you have a multiplicative factor of e to the minus s that we'll see in just a minute, what that s corresponds to, you'll find that getting the inverse transform is actually essentially almost impossible. Okay, so we have to do approximations, and so any system with delays in it becomes very hard to analyze. Okay, and in fact, we won't analyze it. I'll just point you to what the problems are, but we won't really talk about systems with delays much at all. And it's a very interesting and very difficult field of analysis when you have systems with delays, which is actually pretty much all practical systems. Okay, so, but at least from the perspective of the transform, it's very easy to write that down. And the other form is time scaling. Time scaling says that if xt, this is the same thing, is true, then x of at corresponds to 1 over mod a x of j omega by a. Okay. So what we're saying is that first let's see what at means. Okay, let's take a value. Let's say x of at is, let's say, the value 5, just to. When you see an equation like this, the easiest thing to do is, okay, let me pick a value, pick a small integer, 5, 2, 10, whatever. Let's say pick 5. What does x of 5t mean, okay, as opposed to x of t? What's happening is that, let's take some signal over here. So I take some signal over here, and I pick some value over here. Let's say this is 1, right? So x of 1 is this value over here, right? Now, this is x of t. What is x of 5t? Okay, what's going to happen is that this value 1 is going to look the same way. Oops, I'm going to try and draw the same thing. It's going to look the same signal because signal isn't changing, right? Except that what is happening at 1 happens here at time point 2, right? Because 5 times 0.2 is 1, and that's happening at x of 1. So this is, okay, what's happening over here at the time 5, okay, is going to happen over here. The same value is going to be basically 1, because that's what x of 5 is, right? So we're multiplying by 5t, you kind of made the signal go 5 times faster. Okay, you kind of compressed it in the time domain. It's going 5 times faster. Okay. I guess I called it slower. So how do I? Okay. So but you can see how this scaling is working over here. In this domain over here, what happens is that we have the inverse of that. So we are going to take x of j omega by a. And so whatever the transform is going to be, we're going to have the opposite direction because we're going to take this direction. So we're going to have everything happening. What happens over here in, let's say this is not going to be, maybe I should draw a different picture just to make sure you're not confusing it. So let's say this in the transform domain is given by some function of omega, okay, something like that with some zero crossings. And this is omega now. Okay, this is also omega over here. So here we have x of omega, and here we're going to have x of omega by a. Okay? So if this value of the zero crossing happens at some value, or let's say omega equals 100 radians per second, now this is going to happen at 20 radians per second. Okay? So in the frequency scale, we're going to see that we're going to have this sort of expansion over here. So what happens if this value, this one happens at, let's say, omega equals 10, then this is going to happen at omega equals 2, because we're dividing by 5. Okay? Oh, wait a minute, I'm doing this right? I always get confused with this stuff here. So let's see. So we have, I'm sorry? It's expand, yeah, I made a mistake here. It should be, oops, yeah, because I'm going to take this value, divide by 5, and then get that. So this is going to be 50, this is going to be 10, this is going to be 50 over here, sorry, this is going to be 500, yeah. Because we're going to divide by a, right? So we're expanding in the time domain, sorry about that. I'm still not over being sick, so I can't really think that straight anymore. Anyway, so here we see that this value is going down. So things are kind of compressing in the time domain, right? What happens in time 1 is happened already in time 2, right? So going to see a movie, it's a 2-hour movie, right? If you have a compression in the time domain, by 20 minutes you've already seen the movie, right? 2-hour movie is 120-minute movie, divide by 5, it's 24 minutes. So in 24 minutes you've seen the movie. It's like fast forwarding through the movie, right? In the frequency domain, we get the opposite. What happens at this angular frequency of 10 is, happening at time 50 and over here. So we get this inverse scaling of time and frequency, okay? And that's the same thing we saw with the Fourier series. When the time period expands, the frequency coefficients come closer together, right? And so we had this inverse. It's always true for all transform domain things. Compression in the time domain corresponds to expansion in the frequency domain, and the other way around. Okay, and we see that over here. So hopefully these two figures explain what the scaling means. So we are going from one, the shape is preserved, but the time looks different. Right, you're just seeing the movie in fast forward, and in the frequency side, we find that the corresponding thing, the frequency is expanded. Right? So if we were to draw this on the same scale, this would be stretched out, okay, 5 times more. And any questions about this over here? Okay. So, right. Okay. So then we come to this thing, this duality, and this is where it gets a bit messy, and I have to admit the notation I'm using here is not very helpful. So anyway, let's see. So duality, it says, okay, if x of t goes to capital X of j omega, then x, the capital X of t goes to 2 pi x of minus j omega. Okay. So it's easy enough to state. What we're saying is that we take this formal parameter j omega and compare it with this formal parameter t, and what we can do is we can replace we can take the function on the right hand side and write it over here, and take the function on this side, write it over there with the factor of 2 pi, and it's going to work. So first of all, let me show you that it's not really magic. Okay, it's really quite easy to show how this happens. And to do this, what we need to do is to see that x of t is given by 1 over 2 pi integral minus infinity to infinity x of j omega e to the j omega what is it d omega. I think I'm leaving out a factor here. Is it j omega t naught? I'm sorry. X of t, yeah, 1 over x of image omega t. Sorry. D omega, right? This is by definition of the inverse Fourier transform. So I can just write this as 2 pi x of t equals this over here. So I can just move 2 pi to the other side. So I'll just do that over here to save some space. And then what I can do is, let's say that I write x of minus t. So 2 pi x of minus t is going to be integral minus infinity to infinity x of so t is going to become negative over here. Everything else is going to be the same. So x of j omega e to the minus j omega t d omega. And now what we do is we just replace the symbol t with omega, okay? Because it's just a symbol, and then we get 2 pi x of minus omega equals integral minus infinity to infinity x of j t e to the minus, this doesn't change, j omega t dt, okay? And this basically is going to okay, so how do I've now managed to get myself into I can't see properly over here. So this basically should be giving us this. So this is x of t. How did I get into this mess here? Okay. I have this equation here. So 2 pi x of t is, okay, so I replace the t by omega, I get this. And now right, so this one over here is this, okay? And so if I flip this around, basically I'm getting that I have this is in the frequency domain, and this corresponds to what's in the time domain over here, okay? Because this is the Fourier transform of a capital X of jt, right? By definition of the Fourier transform, because the definition of the Fourier transform is that x of j omega equals integral minus infinity to infinity xt e to the minus j omega t dt. So I've got exactly that form over here, x of t e to the minus j omega t dt. So I get that over here. So I can replace that as being capital X of t, except that I have this jt over here, x of jt, okay? So this is where I said the notation is getting me into trouble, because I was using the formal notation j omega over here and t, just t, and in the homework question I actually asked you 1 plus jt, and now the question is this j a formal sort of symbol, or does it really mean I have a complex input signal? I think somebody asked that in the homework assignment. To be honest with you, I was using it as a formal symbol. Okay, so I would really, what I should have been asking for you was 1 over 1 plus t. But since I asked you for 1 plus jt, I can now give you the answer from here. Okay, and the reason I can give you the answer from first principles is that I have over here, as you see, x of jt, right? This is x of jt over here. So if you just rewrite this part over here for clarity, I get over here 2 pi x of minus omega corresponds to capital X of jt, right? Do you guys see that? And so let's look at the whole example over here. So the question was, what is the transform of 1 over 1 plus jt? Now we know that e to the power minus t ut corresponds to 1 over 1 plus j omega. Okay? So this is x of t, and this is x of j omega, as I wrote earlier. So what is 2 pi x of minus omega? 2 pi x of minus omega is going to be 2 pi, okay, e to the omega u of minus omega, okay? Because I'm going to replace the t with the, I'm going basically from t to minus omega, so x of, so this is going to be x of minus, let me get this right, minus omega. I'm replacing basically wherever I have t, I replace with the value minus omega, so I get this 2 pi e to omega e to minus omega. And then I want to, over here, replace wherever I see j omega, I want to replace that with, so I want with t, so this should be 1 plus 1 over 1 plus t, okay? Except that this is where, as I said, the notation is bad. In this derivation, I'm getting jt, so I'm going to have to replace jt with this. So what I really should have said in this was that the x of j omega goes to jt, okay, to keep the notation consistent. Okay, then I would have gotten jt as I wanted. But instead, I'm getting 1 plus t. Okay. All this is a complicated way of saying what I really want you to understand is this part over here, and I'll go with that in just a second. And so if your answer looks something like this, 2 pi e to the omega u minus omega, okay, that is correct. On the other hand, if you didn't get the answer, but you thought about it and you got confused, it's my fault. So everybody should give yourself 1 point, okay, because I goofed up on this. Yes?
Can we consider j as a constant a?
It's not correct actually to do that, because j is really it's a formal parameter. Okay, so I'm going to actually, yeah. So in terms of the homework, don't worry about it. I'm going to actually go through this one more time, and now I'm going to tell you where where this formal parameter business gets into trouble. So let's go over here. So we start with xt equals 1 over 2 pi x j omega e to the j omega t dt. This is basically your definition. And so here all I've done is replace these parameters, and I get x of minus omega corresponds to x of jt. Question is, what is j over here? And at this point, honestly, I am kind of ambiguous about how I want to resolve this in the book, because it's a formal parameter at the same time. I looked at 3 or 4 different books, and they all have different notations. Nobody seems to be consistent about what it is. And it shows up over here when we say, okay, is this j really there or not? And I think somebody who asked the question, is t, is that a complex input symbol? Is it a really, I mean, how can you have a complex input? In a physical system, of course, we can't have a complex input, right? But we're just looking at the Fourier transform as a mathematical object. That doesn't really care. So I don't really like the way this is depicted. The only important part is to remember that we can actually do this manipulation of duality, and I'm going to kind of figure it out and come up with a better answer for you, I guess, in the next class. I didn't expect this to be a problem until this morning when I was looking through the homework, and I said, oh, right, what do I do with the formal parameter? Okay, so you had a question.
I think the notation is wrong. It must be x of jt gives 2 pi x of minus omega.
X of jt should be good. Sorry, this one here? Yeah, I know, we can do that. Sure, we can do that. We can have taken up. Oh, you mean this one?
Yeah.
Yeah, so the thing is, you do get x of jt here, correct? But I don't like having x of jt, capital X. I don't like that, because I don't want complex signals of time. I don't mind complex frequencies, but I don't mind complex. So it's not a question of. I mean, I know what the real answer is. This is the math, right? It's you do get x of minus jt, correct? I don't like the way it comes out. So anyway, I'm going to stop here. Yes? I kind of lost where the 2 pi came from. Where the 2 pi came from? So by definition, we have x of t is 1 over 2 pi. This is the definition of an inverse Fourier transform. I just moved it to the left-hand side. That's all. That's where it came from. Okay, so transform of a derivative, I'm just going to let it be because it's not super important. But the important property is the convolution property. And so let's go into convolution property. And really the convolution property is one of the key reasons why we're studying Fourier transforms in the first place. And what it says is that if you have two functions x1 of t and x2 of t in the time domain, and I'm going to convolve them. So I should have written these like this. So x1 of t convolved with x2 of t. Then what I can do is this corresponds to basically x1 of j omega multiplied by x2 of j omega. That's it. Okay, that's the beauty of it. And I haven't given the proof here, but the proof is actually pretty straightforward. So this is nice. Convolution is complicated in the time domain, but in the frequency domain, we can simply do this. And so what this means is that I can take the input to a LTI system. So I have some LTI system which has some impulse response h of t, and it has some input x of t, and the output is going to be x of t convolved with h of t. Instead, what I can do is that I can compute the Fourier transform x of j omega and the Fourier transform of the system h of j omega and say that this is equal to y of t. I can say that x of j omega multiplied by h of j omega is going to be y of j omega, and then I compute the inverse Fourier transform to get y of t. So the steps are basically take the input, find its Fourier transform, find the impulse response, find its Fourier transform, multiply them, and take the inverse, and you're done. Okay, and that makes it very, very straightforward to solve systems. Now, as we'll see in just a moment, the Fourier transform has some problems. You know, it's not always defined because not all functions satisfy the Dirichlet conditions. So we use Laplace instead, but this is exactly what we'll do with Laplace as well and with Z transform. So it's useful to know how to do it. So I'll do an example to show you what it is. Let's say the input to this function is e to the minus t u of t is xt, and this one is given by, and the h of j omega is given by 1 over j omega plus 2. So I've already done the work of telling you what the transform is. It's j omega plus 2. So what is going to be yt? So well, we can do that quite straightforward. So let's look at x of j omega. This one is given by 1 over 1 plus j omega, and that's this. So y of j omega is going to be the product 1 over 1 plus j omega 2 plus j omega. Okay, that's y of j omega just from the convolution property. Because the convolution of the output is, this is just what we learned about a week ago, that we get the convolution of these two, and now we just multiply it out. And now I need to find the inverse transform. To find the inverse transform of something that looks like this, 1 over 2 products, we use a technique called partial fraction expansion. Okay, and how many of you have seen partial fraction expansions before? Okay, most of you have seen it. So I'm going to give you the solution, but when you do control theory, I'll kind of go into partial fraction expansions a little bit more. For now, I'm just going to tell you the answer, and the answer is going to be basically 1 over 1 plus j omega. So y j omega equals minus 1 over 2 plus j omega. And you can just see that this works because you have 2 plus j omega minus 1 minus j omega, so you get 1 over this, so that just works out nicely. Now we use the linearity property to do inverse transform. Because this is linear, we can take the inverse of this minus the inverse of that, and this one is going to be just e to the